All right, let's get into it. Today, we're diving into a field of logic that asks one of the most fundamental and honestly kind of scary questions in all of science.
Think about that for a second. Can a proof, the absolute gold standard for certainty, actually have a hidden contradiction buried inside it? Could the entire magnificent structure of mathematics be built on sand? And believe me, this wasn't just some abstract, late-night thought experiment. This was a full-blown crisis. See, mathematicians had discovered some really weird paradoxes in their theories, and it sent these massive shockwaves through the community. The race was on to secure the very foundations of what we know.
So, to solve this problem, the legendary mathematician David Hilbert came up with this incredibly audacious plan, a plan that would basically change the game for logic forever. This whole thing was called Hilbert's program. And the goal here wasn't just to, double-check a few theorems. No, the idea was to create a system, almost like a machine of pure logic, that could formally prove the consistency of all mathematics.
Hilbert wanted a rock-solid method to show that you could never, ever use the rules of math to prove something absurd, like 0 equals 1. It was this epic quest for absolute certainty. But how do you even begin to analyze a proof itself?
Well, the answer required a complete change in perspective. And the big breakthrough? It came from a young German mathematician who basically gave logic a whole new shape. In this absolute game changer of a paper, Gentzen didn't just add a few new rules. He completely reimagined what a proof even is. He introduced these brilliant new ways of structuring arguments, one called natural deduction, which was designed to work the way we humans actually reason, and another called sequent calculus, a super powerful tool for analyzing the nitty-gritty structure of those arguments. Now this was a huge leap. Before Gentzen, everyone thought of a proof as just a straight line, a list of formulas one after the other. But he saw it as a tree, with the basic assumptions down at the roots and the final conclusion as the trunk. And seeing it as a structure was revolutionary, because suddenly you could analyze the shape and the flow of the logic itself. And just like that, a whole new field was born. Proof theory turned the camera around. It stopped focusing on the things being proved and started looking at the proofs themselves. They became these fascinating mathematical objects you could study with their own anatomy and rules. Okay, so now that he had this new structural way of looking at things, Gentzen created an amazing tool to check a proof's integrity, a way to guarantee it wasn't making any sneaky, unstated leaps of logic. He zoomed in on something called the cut rule. The best way to think of it is as a shortcut in an argument. Instead of building your case from the absolute ground up, you just say, hey, we already proved this other thing over here is true, so let's just use that. It's super efficient, right? But it can also hide a ton of complexity. So Gentzen's brilliant idea was to create a procedure he called cut elimination. And what it does is it systematically unpacks every single shortcut, every one of those black box lemmas, and it expands the proof until it only relies on the most basic, fundamental starting points. It's kind of like taking a really complex app and compiling it all the way down to its simplest machine code. And the result is a cut-free proof. A proof that survives this process is totally pure. It never takes a weird detour through some complicated idea that wasn't already there in the beginning. It's a guarantee of total logical transparency. No hidden tricks allowed. So for decades, this was all very, very abstract stuff, for logicians and mathematicians. But then something absolutely amazing happened. This deep dive into logical structure, it turned out to be the blueprint for something that would completely change the world. Yeah, you heard that right. It turned out that Gentzen's tree-like proofs weren't just a way to describe reasoning. They were also, perfectly, a way to describe computation. This leads to a truly profound idea, something called the Curry-Howard correspondence. And get this, it's a direct one-to-one mapping. A statement in logic is just like a data type in a programming language. A proof of that statement, well, that's a program that creates something of that type. And the most incredible part? That whole process of cut elimination, of simplifying a proof down to its purest form, that is identical to running a computer program. And this isn't just some neat little theory. This stuff is the bedrock of so much modern computing. It's the foundation for logic programming. It's the engine behind the automated theorem provers that check our most critical software and hardware. It's the core of type theory in powerful languages like Haskell. And it's the basis for the lambda calculus itself, one of the fundamental models of computation.
So here's the thing. While Hilbert's original grand program was famously proven impossible by Gödel's incompleteness theorems, the tools that he and Gentzen created along the way gave us something arguably even more valuable.
It gives us a formal language to talk about what makes an argument good, what makes it clear, and what makes it direct. At the end of the day, it's pretty much the science of how we reason. And you can see its influence everywhere. To give you just one example, a single key survey paper in proof theory has been cited in at least 60 other academic works. And we're not just talking about pure math. Those citations are spread all across advanced computer science, which just goes to show how deeply these ideas are still shaping our digital world. So, ultimately, proof theory leaves us with this really profound question to chew on. If by studying the shape of a perfect logical argument, we get a window into the formal structure of reasoning itself, what does that tell us about the structure of our own thought? It's like a map, not just of math, but maybe of the very nature of how we think.